Good day everyone. Today we are going to be looking at a wonderful topic titled logarithms, and let us consider our objectives for this lesson. At the end of the lesson, you will have understood the relationship between indices and logarithms. You'll be able to find the logarithm of any number in the logarithm table, and you will also understand the anti-logarithms and be able to solve calculations in logarithms. So before we continue, let's just take a brief introduction to know what logarithm is all about. We say the logarithm to base a of a number p is the index x to which a must be raised to equal to p. Okay, let me just relate this to our index so that you will understand the points we are trying to discuss here. See, we have a number a raised to the power of x to be equal to p, where x is the index. We all know that the index is the power as we've defined it in our lecture last week. And the log, what if we are looking for the logarithm of p from this index form? Our log p base a, our log p base a will be equal to x. This means that the logarithm of p is the base, is expressing a as the base and the index as the result. Let's look at a valid integer. Writing 2 raised to power 3, we know our 2 raised to power 3 is in its index form, and the answer is going to give us 8. We have our 2 raised to power 3 to be equal to 2 times 2 times 2. Our 2 times 2 is 4, and our 4 times 2 is 8. Now, for this index form, we all know that 2 raised to power 3 is 8. Definitely, the logarithm of 8 to base 2 will be equal to 3. So the logarithm of a number is directly related to the index form of that number. So that's just the exact thing that we have defined in the statement of above, in the definition above. When we have the logarithm of 8 with the 2, which is the base in the index form, expressed as the base in the logarithm form, but the result of the index form is the logarithm that we are looking for, while the index actually is the result of its logarithm form. So the index of 2 raised to power 3 is 3, the result is 8, and the logarithm of 8 will be to the base of 2 to give us 3. Let us consider another example for us to have a better understanding of the concept of indices, of logarithms rather. Looking at another index form here, let's consider 4 raised to power 3, which equal to 64, because 4 times 4, 16, 16 times 4 will give us 64. 4 raised to power 3, which is 64. Here, the logarithm of 64 will be to the base of 4, which will give us 3. It simply means this equation that we have above here is the index form, while the one we have below here is the logarithm, the log form, logarithmic form, also known as the log form. So whenever you see any expression in index, taking it to the logarithmic form is just expressing that power, that index, as the result, and expressing the base as the base of your result in the index form. So 64 is the result in the index form, and the logarithmic form we have the base the index form expressed as the base here, and the index expressed as the log. So for every index expression, the result is always the direct log number, and for every log number, the result is always the direct index of that particular number. Just like I've explained earlier, the relationship between indices and logarithm. When we have this expression 2 raised to the power 3 to be equal to 8, it is equivalent to log 8 base 2 equal to 3. The 2 raised to the power 3 is known as the index form, while the log 8 base 2 is known as the logarithmic form. So we can change an expression, more like converting an expression from its logarithmic form to an index form, and from the index form to the logarithmic form. Just for us to note that the product of the expression in its index form is also the log number in the logarithmic form. So the product of 2 raised to the power 3 is 8, and the log number of 8 base 2 equal to 3. Looking at the following expression, so write the following index form in their logarithmic form. 5 raised to the power 3 equal to 125. We all know that our 5 raised to the power 3 is in the index form, so I'm just going to take this back to the logarithmic form. We have a 5 raised to the power 3 to be equal to 125. 5 times 5 gives us 25. 25 times 5 gives us 125. So definitely the log of 125 to base 5 will be equal to 3, because we are taking it from the index form to the logarithmic form. So this is the logarithmic form, this is the log form of the index expression given, and for us to take this back to the index form, it's very easy. We just express we raise 5 to the power of 3 to give us 125. Okay, taking an expression from its logarithmic form to its respective index form, we are given log 32 base 2 to be equal to 5. It means this 5 will be expressed as the index of 2. That means we have 2 raised to the power of 5 to be equal to 32. So that is basically how to convert your expressions from its respective index form to its equivalent logarithmic form. Common logarithms. What do we call common logarithms? Logarithms used in calculations are normally in base 10. Writing log 1000 to be equal to 3 is the same thing as writing log 1000 base 10 equal to 3, because when you convert this to its index form, it will be 10 raised to the power 3. And our 10 raised to the power 3 will be 10 times 10 times 10. We have our 10 raised to the power of 3 to be equal to 10 times 10 times 10. 10 times 10 is 100. 100 times 100 is 1000. So the reason why we call it the common logarithm is that we don't really have to write the base 10 anytime we're expressing a number or we're writing a number in its common logarithm. There's no need to write down the base when using common logarithms. Once you see a log number in which the base is absent, it automatically means that number is in base 10. So our log 10 equal to 1, because we have So while we are treating indices in one of the laws of indices, the zero index law, said anything raised to the power of 0 equal to 1. Here we have the log 10 to be equal to 1. Okay, let's start from log 1 to be equal to 0. Here it means this is 10, and automatically the index form will be equal to 10 raised to the power of 0. And you know anything raised to the power of 0 will give us 1. So it's the log 1 that we have at the back. Here in the second example, we have log 10 to be equal to 1. Log 10 equal to 1. You know that this is a common logarithm. The 10 at the base is not written, so this definitely is the same thing as 10 raised to the power of 1, which is 10 itself. That is 10. So dealing with the third example here, we have 10 log 100 rather, log 100 to be equal to 2. Log 100 to be equal to 2. This log 100, without writing the base, we automatically know that this is in base 10. So this means in its index form it is 10 raised to power 2, which is 10 times 10, which is 100. So our log 100 equals to 2. And one thing about dealing about numbers in common logarithm is that when we have a number in its common log in base 10, we all know our log 1 to be equal to 0 and our log 10 to be 1. Any number, any log number that comes between log 1 and log 10 will be in decimal fraction. It will be a fraction, will be in decimal places. You know, between log 1 and log 10, we can have log 2, log 3, log 4, log 5, log 6, log 7, log 8, and log 9. The logarithm between log 2 to log 9 will always be in 0 point something, but it will always be in fraction. We always have decimal at the back, because the next whole number is at log 10, which is 1. So numbers, the result of the number that you are going to get between log 1 and log 10 lies between 0 and 1. We've come to the end of our lesson today. Thank you for your time and patience, and don't forget to like the video and click on the subscribe icon so that you get notifications about the next course as we continue our logarithm, because that's where we are going to stop this week. So next week we are going to continue logarithm as we look at more calculations, look at how to use our logarithms to calculate the logarithm of numbers.